Hey everyone, it's Mr. Mott. What we're going to do today is go through acid-base reactions and how to write your net ionic equations. Specifically, you're going to be focusing on a situation where you have like a strong base and a weak acid. Strong acid and strong base reactions tend to be very straightforward, making water and a salt. So let's check it out. First thing you want to be able to do is know your strong acids and strong bases. Normally for your strong acids, you're looking at 6 of them, but sometimes you'll see chloric acid as a 7th. So for these, your strong acids, you're just going to have to memorize them. For your strong bases, you can use your periodic table to help kind of locate them. So the ones that are highlighted there, they kind of make a lowercase b shape, are your strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. Only ones you really don't encounter too much in practice are rubidium hydroxide and cesium hydroxide. So let's check out a situation where you have a strong base, sodium hydroxide, and a weak acid, phosphorus acid. So what you want to think about with a strong base is that it's going to completely dissociate in water. Okay. Now that hydroxide group is your reacting species, and so what that's going to do, it's going to rip off one of our hydrogens of our weak acid. Okay. So the H plus our OH is going to make water, and then we're going to have our salt that is aqueous. Okay. Now when we write our complete ionic equation, we want to write it such that your sodium and your hydroxide ion are completely dissociated from each other, completely separate. We keep our weak acid together because only a very small portion of those hydrogen ions from your weak acid would actually dissociate. So we write them together, representing that. On the product side, we see that your sodium ion and your dihydrogen phosphite ion are written separate because they're aqueous in solution. Okay, the reason I know it's aqueous, you'd have to check your solubility rules. Okay, from your complete ionic equation, we're going to get rid of our spectator ions, which are your sodium ions. Okay, so getting rid of those, this is our net ionic equation that we have left over. All right. Only showing our reacting species forming water and our resultant ion, H2PO3 with a 1- charge. All right, so that was a situation where we had equal volume and equal molar. Let's check out a situation where we have an excess of the sodium hydroxide. So with this excess sodium hydroxide, we can visualize that we have lots and lots of hydroxide ions to react with all of the hydrogen ions that are in our acid. So if we have multiple OH ions, then we can rip off more of those hydrogens. In our beaker, I'm only noting that we've got one sodium ion. From our previous example, we know that sodium ion is going to be a spectator ion, so I'm not super concerned about putting them in our visual image there. All right. So if we have excess hydroxide ions, we're going to rip off all of those hydrogen ions. And so each time our OH reacts with an H, we're going to make water, and then we're going to be left with our sodium phosphite. Our complete ionic equation from there is going to represent our strong base separated again, and then we are also going to separate our Na3PO3 because that is aqueous in solution. All group 1A elements like sodium are going to be soluble in water. Again, taking away our sodium ions, we are left with our net ionic equation. All right. So let's try another example, and feel free to pause this and try these on your own as we kind of go through them. So here's another example of sodium hydroxide reacting with a weak acid. Okay, so our weak acid, sulfurous acid. Again, if we have equal volume, equal moles, our 1-hydroxide is going to react with one of our hydrogens. It's going to form water and our salt. From here we have our complete ionic equation separating our strong base and separating out our aqueous NaHSO3. From here again, sodium, a common theme, sodium is a spectator ion, and we are left with our net ionic equation, the hydroxide ion reacting with our weak acid, making water and HSO3-. Similar example, now we have excess hydroxide, so now we can pull off both of those hydrogens. Again, we're going to be making water from each of those OH-H combinations and left with Na2SO3 aqueous. Separating out our strong base, and our aqueous on our product side. Na2SO3 is now separate. And again, sodium ions are your spectator ions. Very, very common theme you're going to note. So separating those out and then getting rid of our hydroxide, we are left with our net ionic equation. So one of the big things that you want to make sure that you know are your strong acids and your strong bases. We want to represent our strong base as being separate ions in solution. That's why they're considered strong, because they completely dissociate. And then we want to pay attention to if we have equal volumes and equal molar, or if we have maybe excess of our strong base. Thanks for watching, everyone.